Thermodynamics. Thermodynamics is the study of energy and how it moves between different forms and systems. Think of it like understanding how heat engines work, why refrigerators cool, and how stars burn. It's all about the principles that govern energy transformation and transfer, making it a key part of physics and engineering. It boils down to how energy changes, moves, and affects matter. To fully appreciate the evolution of thermodynamics, let's take a step back and explore its key milestones throughout history. 1593, Galileo Galilei invents one of the first thermoscopes, also known as the Galileo thermometer. 1650, Otto von Guericke builds the first vacuum pump. 1660, Robert Boyle discovers Boyle's law, relating the pressure and volume of a gas. 1676 to 1689, Gottfried Leibniz develops the concept of vis viva, a precursor to the conservation of energy. 1698, Thomas Savery patents an early steam engine. 1738, Daniel Bernoulli publishes Hydrodynamica, initiating the kinetic theory of gases. 1761, Joseph Black discovers that ice absorbs heat without changing its temperature when melting. 1783, Antoine Lavoisier discovers oxygen and debunks the phlogiston theory. 1798, Count Rumford, Benjamin Thompson, publishes his paper on frictional heat, challenging the caloric theory. 1824, Sadi Carnot introduces the Carnot cycle, laying the groundwork for the second law of thermodynamics. 1848, William Thomson, Lord Kelvin, introduces the concept of absolute temperature. 1850, James Prescott Joule proves the mechanical equivalent of heat, supporting the first law of thermodynamics. 1855, Rudolf Clausius introduces the concept of entropy. 1876, Willard Gibbs develops graphical methods to predict the spontaneity of processes. 1900, Max Planck introduces the quantum theory, laying the foundation for quantum thermodynamics. We've made a detailed video about quantum mechanics. I recommend watching it after this video. 1905, Albert Einstein explains the photoelectric effect, contributing to the understanding of energy quantization. 1918, Ludwig Boltzmann's work on statistical mechanics is further developed, linking microscopic and macroscopic properties. 1920s, Sachendra Nath Bose and Albert Einstein develop Bose-Einstein statistics, leading to the discovery of the Bose-Einstein condensate. 1930s, Enrico Fermi and Paul Dirac develop quantum mechanics, which integrates with thermodynamics. 1940s, Richard Feynman introduces path integral formulation, advancing statistical mechanics. 1950s, John von Neumann's work on quantum statistical mechanics. 1960s, Rudolf Peierls and Freeman Dyson contribute to the understanding of phase transitions and critical phenomena. 1970s, Leonard Susskind and Hawking explore black hole thermodynamics, linking thermodynamics with general relativity. 1980s, Gibbs free energy and chemical potential are further applied in chemical thermodynamics. 1990s, advances in non-equilibrium thermodynamics and thermodynamic irreversibility. 21st century. Non-equilibrium thermodynamics, significant progress in understanding systems far from equilibrium. Quantum thermodynamics, insights into energy transfer at microscopic scales. Sustainable energy, developments in thermodynamic cycles for improved power generation efficiency. Nanotechnology, applications in developing new materials at the nanoscale. Biological systems, thermodynamic principles applied to biological processes and ecosystems. This timeline captures the evolution of thermodynamics from its early discoveries to modern advancements. Now that we have an overview of the development of thermodynamics, let's delve into the basic concepts that form its foundation. System and surroundings. In thermodynamics, a system refers to the specific part of the universe that we are analyzing or observing. The surroundings are everything else outside the system that can interact with it. System, this could be as small as a single gas in a container or as large as an entire engine. The system is defined by its boundaries, which can be real, like the walls of a container, or imaginary, like an invisible line drawn around a region of space. Surroundings, everything external to the system that can interact with it. For example, if the system is a cup of coffee, the surroundings would include the room, the air, and anything else that might affect the coffee's temperature. Types of systems. Open system can exchange both energy and matter with its surroundings. Example, a boiling pot of water where steam can escape and heat can be exchanged with the environment. Closed system can exchange energy but not matter with its surroundings. Example, a sealed container of gas where heat can transfer in and out but the gas stays inside. Isolated system cannot exchange energy or matter with its surroundings. Example, an insulated thermos flask approximates an isolated system. State functions. State functions are properties that depend only on the current state of the system and not on the path taken to reach that state. This means that regardless of how the system arrived at its current condition, the value of a state function is determined solely by the system's current state. Examples of state functions. Temperature, T, measures the average kinetic energy of particles in the system. Pressure, P, the force exerted by the particles of the system per unit area. Volume, V, the space occupied by the system. Internal energy, U, the total energy contained within the system, including kinetic and potential energies of the particles. Enthalpy, H, the total heat content of the system at constant pressure. Entropy, S, a measure of the disorder or randomness of the system. Key properties of state functions. Independence from path, the value of a state function is determined only by the state of the system, not by how the system arrived at that state. Reproducibility, if a system returns to its initial state, the state functions return to their initial values. Understanding these concepts is essential for analyzing and predicting the behavior of thermodynamic systems. They form the foundation upon which the laws of thermodynamics are built. Now that we've covered the foundational concepts of thermodynamics, let's delve into the specific laws that govern how energy and heat behave in various systems. Thermodynamics is the study of energy, heat, and how they interact with matter. Think of it as the grand playbook for understanding everything from steam engines to the melting ice cream cone on a hot day. Zeroth law, if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This essentially sets the groundwork for temperature measurement. First law, energy conservation. Energy cannot be created or destroyed, only transferred or transformed. So, whatever you put into a system, it remains in some form or another. Second law, entropy, or disorder, always increases in an isolated system. Energy naturally spreads out, which is why ice melts in warm water but doesn't spontaneously form ice. Third law, as a system approaches absolute zero, the entropy approaches a constant minimum. Essentially, you can't actually reach absolute zero because it would take an infinite number of steps. The laws of thermodynamics provide us with a foundational understanding of how energy behaves in the universe. From the orderly transfer of energy to the inevitable increase in disorder, these laws govern countless natural and engineered processes. Whether it's the engine of your car or the melting of ice, thermodynamics is at play, quietly orchestrating the flow of energy in everything around us. Having explored the fundamental laws that govern thermodynamics, let's delve into the specific processes that showcase how these laws operate in real-world scenarios. Thermodynamic processes describe how systems change from one state to another through energy and work interactions. They play a crucial role in our understanding of physical systems and engines. Isothermal process, this occurs when a system undergoes a change at a constant temperature. Heat is allowed to flow in or out of the system to keep the temperature steady while the system's volume and pressure might change. Think of slowly compressing or expanding a gas in a container while maintaining its temperature. Adiabatic process, in this process, no heat is exchanged with the surroundings. The system is perfectly insulated, so all changes in internal energy come from work done on or by the system. For example, when a gas is rapidly compressed or expanded without heat transfer. Isobaric process, this is when the pressure of the system remains constant. Heat is added or removed from the system, causing a change in temperature and volume. Imagine heating gas in a piston cylinder device where the piston can move freely to maintain constant pressure. Isochoric process, here, the volume of the system stays constant. No work is done since the volume doesn't change, so any heat added or removed from the system directly changes its temperature. Think of heating gas in a rigid, sealed container. These processes, isothermal, adiabatic, isobaric, and isochoric, highlight the different ways energy can be transferred and transformed in a system. They form the backbone of many practical applications in engineering, from designing engines to understanding natural phenomena. Each process tells a different story of how a system interacts with its surroundings. Having navigated through the various thermodynamic processes, let's now explore how these processes interplay within the fascinating realm of thermodynamic cycles. Thermodynamic cycles are processes that return a system to its initial state, making them crucial for understanding engines and refrigerators. Here's a rundown of some key cycles. 1. Carnot cycle. This is an idealized cycle that provides the maximum possible efficiency. It consists of two isothermal processes, where temperature is constant, and two adiabatic processes, where no heat is exchanged. It's more of a theoretical benchmark since real engines can't achieve this efficiency. 2. Rankine cycle, commonly used in power plants. This cycle involves phase changes of a working fluid, typically water. It includes for processes isentropic compression, isobaric heat addition, isentropic expansion, and isobaric heat rejection. The steam engine is a classic example. 3. Otto cycle. This cycle is used in internal combustion engines, like the ones in cars. It consists of two adiabatic processes, compression and expansion, and two isochoric processes, constant volume. The fuel-air mixture is compressed, ignited, and expanded to perform work. 4. Diesel cycle, similar to the Otto cycle but used in diesel engines. It includes adiabatic compression, isobaric combustion, constant pressure, adiabatic expansion, and isochoric heat rejection. The key difference is that combustion occurs at a constant pressure rather than a constant volume. 5. Refrigeration cycle, also known as the vapor compression cycle. This is used in refrigerators and air conditioners. It includes isentropic compression, isobaric condensation, isenthalpic expansion, and isobaric evaporation. The refrigerant absorbs heat from the inside of the fridge and releases it outside, keeping your food cool. Each of these cycles showcases different ways to convert heat into work or work into heat, driving a multitude of practical applications in our daily lives. Building upon our understanding of thermodynamic cycles, let's dive into how these principles power everyday devices like heat engines and refrigerators, which are practical applications of these cycles. Heat engines and refrigerators are practical applications of thermodynamic principles that play vital roles in our daily lives. They demonstrate how energy can be harnessed and manipulated to perform work or maintain temperatures. Heat engines. These devices convert thermal energy into mechanical work. Here's how they typically work. Heat is transferred to a working fluid, like steam in a steam engine, causing it to expand and perform work, like moving a piston. The working fluid then releases leftover heat to a cooler reservoir, completing the cycle. Think of your car engine, where fuel combustion produces heat that pushes pistons and drives the car. Refrigerators. On the flip side, refrigerators work on the principle of removing heat from a low-temperature area and releasing it to a higher-temperature area. The cycle includes four key steps. 1. Compression. The refrigerant gas is compressed, increasing its pressure and temperature. 2. Condensation. The hot gas releases its heat to the surroundings and condenses into a liquid. 3. Expansion. The high-pressure liquid refrigerant passes through an expansion valve, dropping in pressure and temperature. 4. Evaporation. The cold liquid refrigerant absorbs heat from the inside of the fridge, evaporating back into a gas and cooling the interior. These two systems illustrate the versatility of thermodynamic principles, whether it's making your ice cream stay frozen or powering your daily commute. Understanding heat engines and refrigerators showcases how we harness and control energy to enhance our lives. With a clear understanding of how heat engines and refrigerators harness thermodynamic principles, let's dive deeper into the concept of entropy, which plays a crucial role in these processes and the direction of energy flow. Entropy is a fundamental concept in thermodynamics that measures the level of disorder or randomness in a system. Understanding entropy helps us grasp the natural tendencies of energy distribution and its far-reaching implications. Measure of disorder. Entropy quantifies the amount of disorder in a system. For instance, a highly ordered crystal has low entropy, while a gas with particles freely moving around has high entropy. The more ways a system can be arranged, the higher its entropy. Second law of thermodynamics. This law states that the entropy of an isolated system always increases over time. In practical terms, it means energy naturally disperses or spreads out, leading to more disorder. Second law applications. Heat transfer. Heat flows from hot to cold objects, increasing the overall entropy. Think of an ice cube melting in warm water. Engine efficiency. No engine can be 100% efficient because some energy is always lost as heat, contributing to entropy. Refrigeration. Refrigerators work by moving heat from a cooler to a warmer place, increasing the total entropy of the system. Microscopic view. On a molecular level, entropy quantifies the number of possible ways a system can be arranged. A solid crystal has low entropy because its particles are in a highly ordered state, while a gas has high entropy because its particles are free to move around in many different ways. Implications. Entropy has far-reaching implications, from explaining why time flows in one direction to determining the efficiency of heat engines. It's a key player in understanding the arrow of time, as processes naturally evolve from states of lower entropy to higher entropy. Entropy, as a measure of disorder, is a cornerstone of thermodynamics. It underscores the natural trend towards greater disorder and helps explain the efficiency limits of engines and cooling systems. Through entropy, we understand the fundamental direction of energy flow and the inevitable increase in randomness in our universe. With entropy highlighting the fundamental tendency toward disorder, let's explore the equations of state that precisely describe the relationships between different state variables in thermodynamic systems. Equations of state, EOS, are mathematical expressions that describe the relationships between different state variables like pressure, P, volume, V, and temperature, T, of a substance. They help us understand and predict the behavior of materials under various conditions. Let's cover some key EOS. Ideal gas law. This is the simplest EOS, assuming no intermolecular forces and that gas molecules occupy no volume. It's given by PV equals nRT, where P is pressure, V is volume, N is the number of moles, R is the universal gas constant, and T is temperature. Van der Waals equation. This equation corrects the ideal gas law for intermolecular forces and the finite size of molecules. It's given by \left P plus \frac A V squared \right V B equals RT, where A and B are constants specific to each gas, accounting for intermolecular attractions and molecular volume, respectively. Virial equation of state. This expands the ideal gas law to include higher-order terms that account for intermolecular interactions more accurately. It's written as PV equals nRT \left 1 plus \frac B V plus \frac C V squared plus \L dots \right, where B, C, etc. are virial coefficients specific to the gas. Redlich-Kwong equation. This is another modification of the ideal gas law, providing a good balance between simplicity and accuracy for many gases. P equals \frac RT V B \frac A \sqrt T V V plus B, where A and B are again specific constants for each gas. Benedict-Webb-Rubin BWR equation. This is a more complex EOS, used for precise calculations involving real gases. P equals RT \left \frac N V \right plus \left B _ 0 RT A _ 0 \frac C _ 0 T squared \right \left \frac N V \right _2 plus B \left \frac N V \right 3 plus a \left \frac N V \right 6 plus \frac C \left backslash frac n v backslash right caret 3 t squared backslash left 1 plus backslash gamma backslash left backslash frac n v backslash right caret 2 backslash right e caret backslash gamma backslash left backslash frac n v backslash right caret 2. Each of these equations provides a different level of approximation to the behavior of real gases and fluids, making them invaluable tools in fields ranging from engineering to environmental science. Now that we've dissected the equations of state that define the relationships between key variables in thermodynamic systems, let's turn our attention to phase transitions and the fascinating ways matter changes states under varying conditions of temperature and pressure. Phase transitions are transformations between different states of matter, solid, liquid, gas, and plasma, due to changes in temperature and/or pressure. These transitions are driven by variations in energy and entropy. Types of phase transitions. 1. Melting, fusion, the process where a solid turns into a liquid. As heat is added, the substance absorbs energy, which breaks the ordered structure of the solid, leading to a liquid state. 2. Freezing, solidification, the reverse of melting, where a liquid turns into a solid. Here, the substance releases energy, forming an ordered solid structure as it cools. 3. Vaporization, evaporation, or boiling, the process where a liquid turns into a gas. This happens when a liquid absorbs enough energy to overcome the intermolecular forces holding it together. 4. Condensation, the reverse of vaporization, where a gas turns into a liquid. This occurs when a gas loses energy, and the intermolecular forces pull the molecules closer to form a liquid. 5. Sublimation, the direct transition from a solid to a gas, without passing through the liquid phase. Dry ice, solid sublimating into gas is a common example. 6. Deposition, the reverse of sublimation, where a gas turns directly into a solid. Frost formation is an example, where water vapor deposits as ice. First-order versus second-order transitions. First-order transitions involve a latent heat change and a discontinuous change in entropy. For example, melting and boiling involve a latent heat change as energy is absorbed or released. Second-order transitions, no latent heat change and a continuous change in entropy. Examples include the transition in magnetic materials at the Curie point where magnetic properties change continuously. Understanding phase transitions is crucial for many scientific and industrial processes, from designing refrigeration systems to material science applications. They illustrate how matter can change states based on energy and entropy variations, providing insight into the dynamic behavior of substances. Having explored the intriguing realm of phase transitions, let's now delve into the vital concepts of work and heat, which form the backbone of energy transfer in thermodynamic systems. In thermodynamics, work and heat are the primary forms of energy transfer within a system and between a system and its surroundings. Understanding these concepts is crucial for analyzing and designing thermodynamic processes. Work is the energy transferred when a force is applied over a distance. In thermodynamics, it often involves the expansion or compression of a gas within a system. Mathematically, it can be expressed as W equals \int P dV, where P is the pressure and dV is the change in volume. Positive work is done by the system when it expands, and negative work is done on the system when it is compressed. Heat is the energy transferred due to a temperature difference between the system and its surroundings. Unlike work, heat transfer occurs due to the random motion of molecules. It can be described using the equation Q equals mc/delta T, where Q is the heat added or removed, m is the mass of the substance, c is the specific heat capacity, and \delta T is the change in temperature. First law of thermodynamics. This law relates the internal energy change \delta U of a system to the work done by the system \W and the heat added to the system \Q \delta U equals Q, W. This equation signifies that the internal energy change is equal to the heat added to the system minus the work done by the system. Types of work and heat transfer. Isothermal work. In an isothermal process, constant temperature, the work done can be integrated as W equals nRT/ln/frac V_F V_I. Adiabatic work. In an adiabatic process, no heat transfer. The work done is given by W equals \frac P_1 V_1 P_2 V_2 \gamma 1, where \gamma is the heat capacity ratio. Conduction, heat transfer through a solid medium due to temperature gradient. Convection, heat transfer due to fluid motion. Radiation, heat transfer through electromagnetic waves. Work and heat are the cornerstones of energy transfer in thermodynamic systems. Their interplay determines the efficiency and behavior of processes, from engines to refrigerators. Understanding these concepts allows for the practical application and optimization of thermodynamic systems in various fields of science and engineering. With a solid understanding of the fundamental concepts of work and heat, let's explore the diverse and impactful applications of thermodynamics that shape our daily lives and technological advancements. Thermodynamics isn't just a theoretical science, it has practical applications that touch nearly every aspect of our lives, from the mundane to the magnificent. Power generation, one of the most prominent applications, is in power plants. Whether it's coal, natural gas, nuclear, or renewable sources, thermodynamic cycles like the Rankine cycle are used to convert heat energy into electrical power. This energy then powers our homes, businesses, and industries. Engines and transportation, internal combustion engines in cars, trucks, and planes operate on principles like those in the Otto or diesel cycles. These engines convert chemical energy in fuel into mechanical work, propelling us across the globe. Refrigeration and air conditioning. Refrigerators and air conditioners are ubiquitous applications of thermodynamics. They use cycles like the vapor compression cycle to transfer heat from a cooler area to a warmer area, keeping our food fresh and our homes comfortable. Chemical industry. Thermodynamics guides the design and optimization of chemical reactors and processes, ensuring efficient production of everything from pharmaceuticals to plastics. The principles help in understanding reaction spontaneity, yield, and equilibrium. Environmental science. Thermodynamics plays a critical role in understanding and mitigating environmental impacts. It helps model climate change, predict weather patterns, and develop technologies for cleaner energy and waste management. Biological systems. Even biological processes are governed by thermodynamic principles. Metabolism, cellular respiration, and photosynthesis all involve energy transformations that can be analyzed thermodynamically. Material science. Thermodynamics is essential in the development of new materials. Understanding phase transitions, like the melting and solidification processes, is crucial in creating materials with desired properties for various applications. Thermodynamics is a cornerstone of modern science and technology. Its principles are applied in power generation, transportation, refrigeration, chemical production, environmental science, biology, and material science. Understanding and harnessing these principles allow us to innovate and improve the technologies that drive our world. To sum up, thermodynamics is a fundamental branch of physics that explores how energy and matter interact. It provides crucial insights into the nature of energy transformations, guiding everything from the functioning of heat engines and refrigerators to the behavior of biological systems and environmental processes. Through its principles, encompassing laws, processes, cycles, and concepts like entropy, thermodynamics reveals the universal tendencies towards energy dispersion and equilibrium. Its applications span across numerous fields, making it an indispensable tool for scientific discovery and technological innovation. Understanding thermodynamics equips us with the knowledge to harness energy efficiently, leading to advancements that profoundly impact our world. Please remember to subscribe, like the video, and share it with your friends. Your support is greatly appreciated.